All right, homework from last night, page 268. We have 5 questions that we want to go over here, starting with question number 8. Number 8 says a 1,500 kilogram car is making a turn with a 100-meter radius on a road where the coefficient of static friction is 0.70. What's the maximum speed of the car so that it doesn't skid? Well, this is one of those questions where clearly the object is going in a circle. Clearly, because the object is going in a circle, there's a centripetal force involved. Okay, centripetal force, mv squared over r. But that centripetal force we know is always caused by something. We don't always need to know necessarily what it's caused by, but it will always be caused by something. What's it caused by here? Just in case we need to know, what is it caused by here? What supplies the centripetal force? If we don't have this, then we don't have a centripetal force. What is it? Friction, yeah. You take away friction, you add a patch of ice on that turn, and all of a sudden this car goes off in a straight line. You have no friction, you have no centripetal force. So what we've got here is Fc is equal to mv squared over r, but when we put numbers into that equation, we end up having too many unknowns and we can't solve for maximum speed. So because of that, we try to come up with something else. Since the centripetal force is caused by friction, there's no reason why we can't set the two equal to each other. Now understand, it doesn't mean in every question that you have to set them equal to each other. It's just that we can set them equal to each other because one is caused by the other. If you can solve for the maximum speed with one of the equations or the other, go ahead, be my guest. It'll be the right answer. But if you can't, well, then let's try setting them equal to each other since friction causes the centripetal force. We're going to say mv squared over r equals mu times the normal force, but the normal force here is going to be m times g, assuming we're on a flat horizontal surface. So it becomes mv squared over r equals mu times m times g. Let's cancel out the masses, and we're left with v squared over r is equal to mu times g. We're solving for v, so let's take the r over by multiplying, and we get square root of mu times g times r. So let's see here now. 0.70 times 9.81 times the radius here of 100 meters. When we do that, I think we end up getting 26 meters per second, which is almost 100 kilometers per hour. Anybody have an idea what the designer of a highway could do to increase the maximum speed that a car could go around this turn? What's one thing that the designer of this highway could have done to make the maximum speed 35 meters per second, let's say? Increase the radius of the turn? Absolutely. If you make the turn a bigger radius, then yeah, the car can go faster. Absolutely. Before it starts sliding. What's another thing that they could have done? Yep. Yeah, if they bank the turn, right? When you see a racetrack, they're always, the corners are always banked like big time, right? Like 35 degrees, 40 degrees, like banked a lot. And the reason for that is because they want the cars to be able to go really, really fast and not have to slow down too much when they go around those turns. When you go on a highway around a turn, especially a sharper turn like an on-ramp or an off-ramp, you see them banked as well. Not nearly as much as on a racetrack because you don't want cars to be going 200 miles per hour on a turn on a highway. But they do bank them, which allows cars to go faster. Can anybody suggest to me maybe why a banked turn allows a car to go faster around a turn? Here's the banked turn. We're looking at it from kind of a cross section of it, okay? You guys understand this is the car, the back wheels. Okay, these are the tail lights of the car. Okay, so you're looking at the car from behind here. Which way does the normal force act? Friction is going to act toward the inside, right? Friction is going to act this way. Which way does the normal force act? Straight? Straight which way? Straight down? No, that would be gravity. It's going to act at an angle up like this. Yeah, the normal force is going to act up like this. Look at this. There's a component of the normal force that's acting this way, right? So why does a banked turn allow a car to go faster around a turn? Well, because on a banked turn, you've got friction, but on a banked, just like you do on a flat turn, but on a banked turn, you've also got a component of the normal force that's pushing toward the center of the circle. Does that make sense? So the normal force here, or at least a component of the normal force, is helping friction provide the centripetal force. So because there's more centripetal force there, as a result of that normal force, the X component of the normal force, you can end up going a little bit faster without going off the turn. Make sense? And we won't analyze that, figure out what the speed would be, but that's how you would deal with that. All right, next question we need to go over was question number 12. And number 12 says, determine the centripetal acceleration acting on a person standing at the equator. Good question. There's a couple of people that asked me about this one yesterday as you guys were working on these in class. This is a really good question. One where you got to kind of read between the lines in order to figure out what to do here. All right. Looks like we're missing some stuff here. Looks like we don't have enough stuff to use. A is equal to v squared over r, because in the end, we know that's what we're going to have to use, right? Centripetal acceleration is going to be v squared over r. We know r, okay, but we don't know v. Any suggestions maybe as to how we might tackle that, how we might find the value of the speed? How fast a person is moving when he or she stands on the equator? Okay, v is equal to 2 pi r over t. Seems reasonable. Well, we know the radius, right? Because it's the same radius as we're going to use in the denominator for the acceleration equation. But what's the period? How long does it take a person to go around in a complete circle while on the equator? Yeah, 24 hours, right? The Earth makes one rotation on its axis every 24 hours. So if I happen to be standing right here on the equator, when am I going to be back here again to the exact same spot? Well, when that spot on Earth is back to the exact same spot, when the Earth has made one rotation on its axis, which is 24 hours. So we're going to say the speed is 2 times pi times the radius of the Earth, 6.38 times 10 to the 6, divided by the period, which is 24 hours, which is 86,400 seconds. Where did that number come from? We multiply 24 by 60 to get minutes, and then we multiply it by 60 again to get seconds, and it works out to be 86,400. What is that speed there? Big number. Who's got it? Mary, get that one? 463.96. Anybody else get that? Boy, that's pretty quick, eh? So what we're saying here is if you're standing on the equator, you are at any given moment traveling 464 meters per second. That means you're moving at almost 5 football fields per second. That means you're going almost 1.5 times the speed of sound at any given moment. Mach 1.5 at any given moment. Wow. It's pretty fast. Why don't you feel it? Well, it's over a long period of time. It's over a short period of time too, because at any given instant in time, you're traveling that fast. So why don't you feel that speed? You travel at 900 kilometers per hour in an airplane. Why don't you feel that speed? Because you're not speeding up or slowing down, right? You feel it when you speed up or slow down. Why don't you feel this? Because you're traveling at 464 meters per second all the time. You're not speeding up or slowing down. If the Earth was to suddenly stop spinning on its axis, what would happen to you? You'd probably fly off in a straight line. Right? We're not going to notice it as long as the Earth doesn't speed up or slow down. Okay, then if it does, then that becomes a bit of a problem for us. 463.96, we got to square that, divide it by 6.38 times 10 to the 6. And we get a centripetal acceleration here for question number 12 of 0.0337. Sense? We got a speed of 464 meters per second. We want to go off in a straight line, right? What keeps us from going off in a straight line? Why don't we go off in a straight line here? What provides the centripetal force? Something has to provide the centripetal force. What is it? Gravity. Well, gravity gives us an acceleration of 9.81. How much acceleration does gravity need to give us to keep us on the Earth? 0.0337. It gives us way more than it needs to, right? Way more than it needs to. And that's why we don't fly off the Earth, is because, yeah, we need 0.0337. We got 9.81, so there's no issue with this. No issue with this falling off. Number 13 says an ant climbs onto the side of a bicycle tire at a distance of 0.4 meters from the hub. In other words, this becomes our radius. The 0.010 gram ant, we're going to convert that to kilograms, can hold onto the tire with a force of 4.34 times 10 to the negative 4. What's the frequency? At what frequency would the tire fling the ant off, assuming the wheel spun in a horizontal plane? I think I'm going to say frequency is 1 over the period. I got to get the period. Maybe find the period maybe by what? V equals 2 pi r over t. Okay. So let's get the period there. Oh, wait, we don't know what the speed is. How are we going to get the speed? Well, centripetal force. I have to say F is equal to mv squared over r. All right. Let's solve for v there. F times r over m. Let's square root that. It gives me speed. So it becomes 4.34 times 10 to the negative 4 times the radius of 0.4 divided by the mass of 0.0. Let's tack on 2 more zeros, 3 more zeros. It gets confusing moving the decimal place over, right? I don't know about you, but like here I've been doing this for 22 years. I still get mixed up. When I get confused about where to move the decimal place to, here's what I do. Like I say, I know a gram is 10 to the minus 3 kilograms. So I'm just going to write 0.010 times 10 to the minus 3 kilograms. All I'm going to do is replace the grams with 10 to the minus 3 kilograms. Then I don't have to worry about moving the decimal place over, right? Just punch it into my calculator like that. Square root that. It's going to give me a certain speed, but you're going to plug back into here to solve for period. 2 times pi times the radius divided by that speed. Solve for the period, plug it back into there to solve for the frequency. And when we do, I think number 13 should work out to be 1.7 hertz. 1.7 revolutions per second. Next question we want to go over is number 14. Here's a good one. 2 pulleys are connected together by a belt as shown in the diagram below. The pulley connected to the motor spins at 200 RPMs. What's the frequency of the larger pulley? So this is the one that's connected to the motor, and it's spinning at a frequency of 200 RPMs. What's the frequency of the larger one? What's the frequency of this one right here? They give me a hint here. Maybe they shouldn't have given me a hint here, but they did. It says the velocity at their outer edge is the same. That's not actually quite true. What should they have said? The speed is the same at the outer edge, right? The velocity is always changing, always changing. At any given point, it's different, but the speed is the same at the outer edge. Let's call this pulley number 1 and pulley number 2. If they tell me the speed is the same for both of them at the outer edge, then let's do exactly what they tell me to do. V1 equals V2. Got it? That make sense? right? They told me that. They told me the speed is the same. So just do what they said. All right, V1 would be 2 pi R1 over T1, and V2 would be 2 pi R2 over T2. Is that okay? Can I do that? Sure. They told me the speed is the same. Then 2 pi R over T is the same as well. I get a bit of a break here, right? 2's cancel, pi's cancel, and I'm left with R1 over T1 equals R2 over T2. But wait a second, I got frequency, so I'm going to replace T with 1 over F. So it becomes R1 over 1 over F1 equals R2 over 1 over F2. I can simplify this a bit and say R times F1, because right, R divided by 1 over F is the same thing as saying R times F over 1, right? Divide by the, or multiply by the reciprocal. Somebody in my physics 30 class called it, is it kiss and flip? Is that what they said? Is that what you guys learned in math class? Kiss and flip? Yeah, I never heard that before. My physics 30s told me that that's what they call it in math class. But when I learned this, it was always, look, you're dividing by a fraction, multiply by the reciprocal, multiply by the inverse, or kiss and flip, whatever you do. Do it on the other side as well. Becomes R2 times F2. All right, now it becomes easier, right? R1 is 0.10. F1 is 200. Oh, wait, almost made a mistake there. 200 RPMs. What should that be in hertz? What is it? 3.33 hertz. We were dividing that by 60 to get the number of rotations per second, right? Uh, 0.25 meters is the radius of the bigger one, times F2, and F2 should work out to be 1.3 hertz. Hertz. Now, if we want to convert that back to revolutions per minute, we're going to multiply it by 60. And we can do that. It gives us 80 RPMs. Either one would be fine, though. RPMs or hertz doesn't really matter there. Yeah, how many people got that one? Okay, that's kind of a tricky one, eh? If you had a little bit of trouble down here, I can live with that. Okay, I can live with that, absolutely. But listen, up here, you may have had trouble with that last night, and that's okay if you did. But the takeaway from this is when they tell you something, like the speeds are the same, then do what they say. Okay, if I said right now, put your pens down, then you would know to put your pens down. If they tell you that the speeds are the same, then write down V1 equals V2. They just do what they say. Just like when I tell you to put your pencil down, you put your pencil down. Do what they say. And then see what you can do. See what you can get from that. All right. Our last question that we need to go over here is question number 15, which says, two NASCAR race cars go into a turn beside each other. If they remain side by side in the turn, which car has the advantage coming out of the turn? Now, in all likelihood, they will not remain side by side in the turn. How come? Yep. Good. The vehicle on the inside has less distance to cover. So unless the vehicle on the outside is traveling significantly faster, it's not going to remain in the same position going around that turn, right? When cars pass cars on corners in races, they almost always cut on the inside, right? And they cut on the inside because they're not going. One car is not usually going that much faster than the other car. It's strategy, right? Cut to the inside so you have less distance to travel at roughly the same speed. But let's assume that they do remain side by side, which one would have the advantage coming out of the turn? The one on the, no, the one on the outside. If they remained in the same position. Now, that's a big if, because they probably wouldn't. But if they did, the one on the outside would have the advantage. Why? Because it's going faster. If it remains in the same position, then it's going to be traveling faster than the one on the inside. Okay? The reality is that likely wouldn't happen. Okay? The reality is you want to be on the inside because you probably can't go fast enough to maintain the same position. But if you could, then the one on the outside would have the advantage because it's going faster. Good?